All right, time to start the next talk by Sandro Vaienti from CPT Lumini and Université de Toulon in France. And the title of his talk, by the way, that we also know and love him, so we don't love just the other speakers. And the title of the talk is A Few Results on Quench Random Dynamics on Open Systems. Okay. Thank you very much.
Thank you, Mark. I would like first of all to thank the organizer. I have here the list: Simone, Alfonso, Anna Maria, Marco, Roberto. Yeah. Okay, so let's see how it works. Just a second. Okay. Okay, so this is the fourth part of a project which we started in with my colleagues, which are, yeah, okay, where's the pointer? How does it work? Okay, doesn't know. Okay, this is questo per andare avanti.
Ok, questo qua per andare avanti. Questo qui è il puntatore.
Dove è il puntatore? Qual è?
Questo qui.
E per andare avanti questo?
Quello grande e quello piccolo.
Ecco, okay, so this is the first part of a project which we started 4 years ago with my co-author, which are these Australian guys, Jason Etnick, Gary Froyle, and then Cecilia Gonzalez-Stockman. The idea was, still is, to try to build a thermodynamic formalism for a random dynamical system. You will see this kind of dynamical system are perturbing in what people call quenched way. I will explain what it is. We already wrote 4 papers. 3 papers, which are here, 1, 2, 3. One is published, the other 2 are submitted, and the 4th one we speak today will be put on archive probably this week. Okay, let me briefly remind you what we did in the previous paper. In the first one, we tried we considered potential which are more general than the usual geometric potential. And the idea was to try to get invariant measures in the sense of random setting. I will show you in a moment what it means. And the first problem which we faced 4 years ago, if you choose a potential which are more general than the geometric one, was to construct what people call conformal measure. And it took at least 1 year, 2 years to construct this conformal measure for this kind of perturbed system. Then we tried to get the same for open system where we put holes, and as well it took more than 1 year in order to construct these kind of measures for this open system. And now what we are trying to do is to look at systems still open with small holes, because we are interested in something else which is paired to the large holes which we considered before, and this is just the topic I'm going to speak today. First of all, some brief reminder of what people did in this business. Okay, here you will see in red books, papers, and people who work in this subject. Let me simply point out with a pointer exactly the book by Arnold, Random Dynamics, which is really a source of facts, of theorems, of inspiration for people working in this field of quench dynamical system. Then in the case of thermodynamic formalism, the first result by Kiefer, and then by the German school around Arnold, Bogenschulz, Gundlach, and Kroll, and then by Urbanski and co-authors. In particular, okay, you see the list of people who worked in this field. What we did our first result at the same time of other contribution, in particular by Stadbauer, Varandas, and Zhang. Let me briefly tell you what are the difference between what we did and what this guy did. Okay, so those guys worked with basically one-dimensional dynamics. To be more precise, they also looked at non-invertible in higher dimensional dynamics. We did only one-dimensional dynamics. But what we tried to do, what we did, was to consider one-dimensional maps with discontinuities, which create some problem which this guy didn't have. But still, there are, of course, interesting result of what they got, what we got. about technicalities, we try to generalize to our setting, which is the quotient setting, which I'm going to expose, what we did in the deterministic setting, in particular with Carlangelo and Saussure, and we were also inspired by works by Bussy, who really worked with quotient dynamical system, but only for the geometric potential, namely 1 over the derivative or 1 over the determinant of the Jacobian matrix. And then we were also inspired by what I did with other guys, in particular Froilan, Dragicevic, and Gonzalez-Stockman, where we proposed a technique to obtain the limit theorem using the multiplicative ergodic theorem and the Nagaev-Givarch approach using the twisted operators. I probably will say something at the end. And also we're inspired by other works which are written there. Okay, so let's now start with what we did in the last paper, which I'm going to expose here. Okay, the source of inspiration was a result by Carlangelo and Gerhard Keller, where they gave a perturbation theorem which was really adapted to treat open system, namely system with holes. Okay, let me first tell you that there are two kinds of holes, real holes and fake holes. Both are interesting. In particular, the fake holes comes when you consider some statistical property like recurrence or extreme value theory. Okay, let me first of all state this theorem, which is a very general one. Don't be scared by the bunch of assumptions. There are really a lot, but all these assumptions could be checked easily as soon as I will give you a precise form of the perturbation. Okay, so the idea is the following. We have, since we work with quotient dynamical system, okay, this first result doesn't work with random dynamical system. It's a sequential result. Simply, we have a bunch of operators which are composed of one with each other. Then these operators will become the usual transfer operator in a while. And so we compose this operator, and the omega are mapped one into each other by a map which is invertible, but I don't speak about the ergodicity of this map. There is no measure for this map for the moment. And then we perturb this operator, so we get another composition of operators which are perturbed with respect to the previous one. And the idea now is to get some formula relating the multiplier for the unperturbed operator, which is basically the eigenvalue, but in the sense of quotient operator we see in a moment, and the same multiplier for the perturbed operator. And adapting to the quotient setting, what Carlangelo and Keller did in the deterministic setting, we get this formula, which basically allows you to compare the unperturbed multiplier with the perturbed multiplier divided by the size of the noise, which is some size of the noise, which will be precise in a while. And this is given in terms of an explicit formula. And this quantity here can be computed in some cases. And for people working in a statistic of extreme value theory, this guy here is called the external index. It plays some interesting role even in an application. Okay, so let me try now to state the assumption. I repeat, these assumptions are a lot of assumptions, but they can simplify it considerably as soon as we will precise what kind of perturbation we consider. Okay, so these are the assumptions. Let me tell you the most important one, not all, because some of these assumptions are purely technical. But basically, we need an operator. Thanks to this operator, which I call L omega epsilon, as the pattern for being operator, it will be exactly the same in a few minutes. And so P2 is probably one of the most important assumptions. So we need this eigenvalue problem for the operator and this dual, which is written here. Then we need some other condition which you will recognize as some kind of quasi-compactness for this operator, right? And the other are technical questions. But P2 and P3 are probably the most important one, which we have to prove when we have concrete situations. And then we need something which tell us how the unperturbed operator and the perturbed. Okay, 1 and 2 here, which belongs to P4, are just conditions which allow you to compare the operator and the perturbed operator. You will recognize in 2 here what people call the triple norm. It will be introduced by our friend. It will be more explicit later on when I will give you a precise form for this operator. And then you have other technical conditions which combine all these quantities which give you the strength of the perturbation between them. And then you have all this condition here, and then we have other one, P8 and P9. And in particular, look at this quantity here, which is just, which enters this sum here. Okay, this is an assumption. We have to prove that this limit exists. Okay, in the deterministic setting, in some cases, it's not difficult to prove the existence of this limit. It becomes a little bit more complicated in the random setting, but I will give you example how it works. Okay, and if all these properties are verified, we have this result, which you see allow you to okay, it is again. Okay. Oops, I'm sorry. No. I'm completely confused now. Okay. Okay, so I go back now. Okay. Yes. Yeah. Okay, here. Oh dear. It's complicated. Okay. Yes. Okay, let me do this one. It's much easier. No, I mean, I just want to show that this lambda 0 and lambda omega epsilon were just the multipliers of this operator, which is written in P2. You see? You take P2, you take epsilon equals 0, epsilon equal omega. We have omega epsilon, omega 0. They are the two multipliers which enters this formula here. Okay, this one. Okay, now let's go to see how can we get precise, more easy assumption when we consider randomness. So now I introduce the concept of a random dynamical system. Yes?
Up here it was just sequential.
Sorry?
Up here it was just sequential.
Exactly. Exactly. Now instead, I didn't speak about maps. Now we take maps. For the moment, I don't precise what kind of maps we are using. We attach to each map a transfer operator. I will be more precise in a moment. And okay, now it works in this way. Okay, so now what the probability is just in the choice of the parameter omega. Omega is shifted by some application which I call sigma, which is called the driving system. It moves omega into the space big omega into itself, and this sigma preserves a measure m, which is ergodic. And for the theory, it's very important sigma to be invertible. Otherwise, all this, I don't know if it could work. I mean, it works if sigma is invertible and the measure m is ergodic. Okay, so you can think, and there will be a picture later on, at sigma moving. Suppose the space is the interval, but you can identify the interval as with fibers, and each fiber is marked by omega, so you can move from one fiber to the other. This is just the picture you can find in our book. In some cases, we can tell exactly why it is better to use fiber instead of intervals. I mean, different copies of the same space. But in this case, you can think it's exactly the same space. In particular, is the interval. And then, you know, with this kind of construction, you can construct a skew system, which is a deterministic one, where it acts as is written at the end. Okay, now, okay, here is, you see, we introduce the concept of random measure. Let me tell you something about what I wrote in blue. You see, if you take some Borel set B, you have to prove, I will tell you why, and why it becomes important, that the map which is associated to omega, the measure of this measurable set, this map is measurable. This is not completely trivial. it took some job in our previous paper to prove this condition, to prove the measurability of this condition here. This is particularly difficult when we work in higher dimension. And why this is important? Because since we are doing some thermodynamic formalism, as soon as we construct this measure, which are called equivariant, we have to integrate this measure in order to get the variational principle. But you cannot integrate a function which is not measurable. So the point is to prove the measurability of this condition. In our previous paper, it was possible because this measure came from some representation of our function in terms of an integral. And in this integral, we recognize some function which is measurable, so we get the measurability for free. But in higher dimension, what we are working now is not completely trivial to get the measurability of this condition. Then we introduce the operators, and now the function g is the potential, which is not the usual geometric potential. It can be potential verifying some assumption, which I will tell you in a moment. For the moment, it still is on the abstract level. And then let's continue. Okay, now we go. Okay, this is this is the fiber structure which I told you before. Okay, all the fibers basically are the same copy of the intervals. And now I am going to introduce, at the map sigma, the driving system moves one fiber to the others. But in our case, it still is on the same interval. And then we have to introduce some objects, which are important for the following. Now I am focusing on the system for the moment where there is no holes. So the operator has not been perturbed yet. And for this kind of system, we have to construct this measure, which I called mu omega 0. And this measure is called equivariant. It's written in the last sentence. And in order to construct this measure, it turns out that this measure will be absolutely continuous with respect to another measure, which is the measure nu omega 0, which verifies the first equation. This is called the conformal measure. And okay, this is an object which is not completely trivial to get in this Quenchette setting. And okay, so this is something which must be constructed and which is essential in the following, but we can get it. And now we introduce the holes, because the idea is to do open system. But the holes is defined in the usual way. But now you see the holes depend on the fiber. So when the driving system moves one fiber into the other, the hole could change. And the holes are indexed also by omega. And since we have holes, we have to consider the points on the set which do not fall in the hole as soon as the motion goes on. And so we have to consider what we call the surviving set up to stage n, and also the global surviving set, which are the points which never fall into the holes. Yes?
Sorry, the holes are in the fibers that you, in the picture that you made before?
Yes. Okay. This one? Yes.
Oh, okay. This is the image that I have.
Yes.
Okay.
Yeah. Okay. I projected all, yes, all you see, each fiber brings a hole.
Okay.
And now, and then when you move, when you move the point x with the composition of maps, you see Tj omega send the point into the fiber h sigma j omega, and you have to look at, do not jump into this fiber. And you construct the surrounding set up to time n. And then we get the global surviving set. So we have also some assumption in the paper, some result, not assumption, in order to prove that this is not empty, because otherwise this set could be empty and it's not interesting. And then we define the perturbed operator. Now this is interesting because this is the count of perturbation which will allow us.
This hole can be as large as you want.
Okay, this good question. In one of the paper, in two papers which are still submitted, yes. But in this new one, it must be small because we are using some result of u, and this all. Yes, exactly. This is the content of this paper.
So what about the potential instead?
It comes in a moment.
It comes. I thought I was.
No, it comes. Okay, okay. So, okay, the perturbation is defined in this way. So we look at the perturbed operator is just the previous one applied to a function time the characteristic function of the complement of the whole. As soon as the whole became smaller and smaller, this complement becomes larger and larger, and so this is a kind of perturbation, which will allow us in a few minutes to use some strong perturbative result. Now, I didn't say anything about the potential. We'll come in a moment about the potential. So let's go on. It comes in a moment about the potentials. Now, I promised you that all the previous quantities, which were very complicated to write down in the general functional setting, became particularly simple when the perturbation is just given as I did in the last slide. And in red, I wrote all the previous quantity. It doesn't matter if you don't remember, but this quantity now are very easy to compute, taking into account the count of perturbation, because this perturbation now has a geometrical meaning. I take a function multiplied by the complement of all, so I can check this. This quantity here becomes very easy to check. In particular, look, all these quantities here are given in terms of the closed equivariant measure. Closed means computed without alls. For you see there is omega 0 everywhere when we define this quantity. So it means if we construct this equivariant measure from the very beginning, we can treat this kind of geometrical object when we introduce the perturbation. And now we have a more appealing formula for the external index in terms of geometrical quantities, because here we have the alls, parameters of the alls intersected with themselves, and all this can be really computed in some example, even if the example in some cases are frustrating because they're very simple, but we cannot do better than this for the moment. And now, okay, these are, I continue with the assumption which we can now check on this operator. You see, I spoke before about quasi-compactness and so on and so forth. Now it becomes much more clear. The quasi-compactness now is exactly the quasi-compactness as we mean usually. Don't forget that this operator are quenched operators, so it depends on omega. So you see, this is the reason why we get omega on the left and sigma omega on the right, because we move from one five to the others. The curve correlation. Let me tell you something about the curve correlation, because this is still an open problem. In the previous two papers, when we proved a thermodynamic formula for this kind of map, even for large alls, we were not able to get limit theorems for the following reason: because this CF omega, we cannot prove this L1. If we can prove that this coefficient is L1, we can get the central limit theorem, the almost-sure invariance principle, and so on and so forth. With this, we are not able to prove it. It's strange. In fact, in the next slides, we will take some uniform guy like that, and we can prove all the limit theorem. I will tell you what I mean pretty soon, but this is still open, a problem. We cannot get limit theorem if we cannot prove that this term is at least L1, which is fed to the measure on the driving system, of course. Okay, now look at.
But I'm sorry,
yes.
You never said anything what is the measure on the environment, on omega. So, I mean, it's just ergodic and that's it?
Omega is, yes, only ergodic for us.
Only ergodic.
Only ergodic.
You don't know anything, because
no.
maybe if you know a little bit more, then you use it.
Probably, yes. Yeah, but it's only ergodic. No, we don't go to more important. Yes, absolutely. And now let me keep your attention on the last formula, because the last formula we have exactly the equivariant unperturbed measure of the surviving set up to time n, and this formula will become essential when we compute the statistical properties, especially in particular to extreme value theorem in a moment. This formula is just an adaptation to the quenched setting of what Carlange and Keller did in the deterministic setting. And now, okay, first result. I will come back to the potential pretty soon, but still in this more general framework, the first result is about the escape rate. So the escape rate is the rate at which you fall not into the all. I told you that the surviving set up to time n is x omega n epsilon. We can compute how this measure goes when n goes to infinity, and what it is interesting is in the random setting, this escape rate is the difference between the logarithm of the multiplier for the unperturbed and the perturbed system. And in this case, this formula is true even if epsilon is not small. But when epsilon is small, using some perturbation result, which will come later, we get a formula, asymptotic formula for the escape rate. And this formula here is in terms of what I called before the extremal index. So it gives you information how this escape rate behaves with the size of the noise. And okay, now how we apply this theory to get some formula for the quenched extreme value law. It's a new property. I mean, new is 10 years people worked on this as another way to get statistical information on your system. So basically, you have some observable, which it depends on the fiber, which I call H omega. And okay, on each fiber, there is some points which I take, which I call the Z omega bar, which could be infinity, because this function H omega becomes, let's suppose it becomes infinite in some points. I just look at the distribution of points where this function is, is less than a threshold, which is Z omega, which becomes more and more close to infinity. This is the typical quantity which people study when you look at the extreme value distribution. This theory here is very well understood in the deterministic setting. In the quenched setting, a little bit less, and because there are some assumptions to get. In particular, you cannot hope to get a general result if we don't prescribe something on what I call the Z omega n, which are the threshold. If the threshold doesn't behave in some manner, we cannot get any distribution when n goes to infinity. So the assumption which we did, it works, is the following. So basically, we suppose that the exceedancy with respect to the level set Z omega n verifies what I wrote on the 5 lines. So I keep your attention on T omega because it will give us the asymptotic distribution at the end. Okay, so these conditions here are not very difficult to check if you have a measure which is not atomic, which is our case, because the mu omega 0 are not atomic measure. We can prove it for our kind of systems. Okay, so now the strategy of the proof is very simple. It's written in the last part. Look at the first line. The first line, I'm just looking at point x where my observable is far from the threshold. It's less than the threshold. But this is exactly equal to points which doesn't fall into the hole, and the hole is exactly given by the point where H omega is larger than the threshold. It's just a hole, this one. So for this reason, we can apply the previous theory, and it turns out that we came with this formula here, which is just the formula which we can control with what the theorem which I told you before. And so we get this result. So we get the distribution for the extreme value law and for our kind of observable. And this is not the usual Gamble law because it's a random Gamble law, and it's completely general. And in the formula, the third line, it enters also the extremal index. So basically, we don't care about periodicity. Yes.
Not understand. So this is the probability that you don't see the extreme event up to a certain point.
Yeah, along when you move from 0 to n minus 1.
Yeah.
Yes. Yeah. Exactly. And in particular, this T omega 0, which is called the extremal index, which has this formula which I showed you before, can be computed exactly. Now, let me tell you how we can check all this on very concrete example. Okay, I skip the 18 time. If someone is interested, I can give you some information about the 18 time statistic, which is closely related to what we did before. But now I would like also to answer what Carlangio asked me about the potential. What are the maps which are looking for which we can apply this result? Okay, so first of all, the map are very simple now. Why? Because I want to use some result later on, which I have not stated yet, for which can be applied to this kind of map. For the moment, the assumptions of the map are pretty general. So we have map of the interval again, with bounded derivatives and the number of branches which is finite. And we don't have any expanding condition. It will come in the now. We see why. But for the moment, the derivative is bounded, not from above, and the number of branches is finite. And then as a functional space, we take the bounded variation with respect to the conformal measure, not Lebesgue, because we are doing something general. The potential now is written at the end. Now I come back to that. No, the potential is written in E8, is what we call contractive potential. So basically, we need that if you take the closed potential up to iterated n prime times, is less than the infimum of what is written on the right. Now, if it is the first time you see this kind of condition, you could wonder what does it mean. Okay, so go back, because this condition was introduced by Carlange, myself, and Sossoli in a deterministic paper, sup gn0 less than inf ln0 applied to the function 1, and this is implied by the usual potential, the sup of phi. Phi is the exponential of g, less than the pressure of phi, right? Okay, for people working thermodynamic formally, this last condition is much more familiar, but with Carlange and Benoit, we proved that our condition was more stronger in the sense that we can get much more, and this can be generalized in the random setting for condition E8, which is written there. This is it just can also be checked. Can also be checked in a concrete example. And how can we recover some kind of expandingness by what we call the covering condition? Namely, what basically you need is some interval that could be mapped everywhere, waiting a little bit more. And there are two kinds of conditions. What we use in the previous paper is what we call is this one, which is much more interesting in general. It allows us to cover much more cases. But what we use in this paper, for some uniform reasons, is the third one, is the second one. So it's much stronger than the other one. But because we need some uniformity in order to get what we want. And okay, this is, you see, it means basically we take some interval j, we must find an integer k, such as that for almost all choice of omega, the set is mapped by the composition up to time k over the whole interval. And this also can be checked on some maps. All this, we have example of this. Okay, now let's come. Yes. Yes. Yes, of course. We have okay. We have a bunch of measurability conditions. Yeah, a lot. Yes. Yes. Yeah. This is the functional space is written there. Is BV with respect to the conformal measure. And now I have also another answer to your question. What is now the next step? The next step is to use some perturbation results. Okay, the original result, very important, and deep one, was what Carlange proved with Keller. And this result on Annali of Pisa, everyone knows this result. This result has been generalized to the quenched setting by Eric Riemings in this paper. Stability, okay, you see the title here, there. And we use this result. So basically this result allows you to compare the multiplier for the perturbed and unperturbed system, provided epsilon is small, and also the eigenfunction of the unperturbed and perturbed operator, provided you verify some assumption, of course. And also it gives you some relation on the decrease of this operator Q, which is 0 when you are on the complement of the dominant eigenspace. And so the idea is to use this result, which generalized what Carlange and Keller did in the deterministic setting. This result is proved in the random setting under a lot of assumptions, of course. And we prove that we can fit this assumption of this paper. And basically, there are two steps if we want to apply the Kriening's result. The first step is to prove some Lasotto-York inequality for all epsilon, provided epsilon is small. And then to prove that the perturbed and unperturbed operator are close in this triple norm, which again we use. Okay, now this is a technical issue, just to answer Carlangelo's questions. Kriging's results are stated when he takes the bounded variation with respect to Lebesgue. Instead, what we used was the BV function with respect to the conformal measure. And we proved these two norms are equivalent. But why? Because our conformal measure was adapted to it. I mean, we could prove that the BV norm given by our measure was basically equivalent to the norm given by Lebesgue. This is not anymore true when we put the noise. In fact, the last theorem, you will see we have some issue in order to get a limit theorem for the conformal measure for the perturbed system, because this equivalent, we are not able to prove it exists anymore. Anyway, now let's see to our final result, which collects more or less all what I did, but in the framework which I stated at the end. So when we can apply this Kriging result, which requires a lot of assumption, in particular uniformity assumption, in particular the decay of correlation must be uniform in omega. So what we get are, okay, I will list all the results. Okay, so first of all, you see now we have epsilon everywhere. So we can prove we have this eigenvalue problem for the perturbed operator, and rho omega epsilon is the multiplier, and h is the density. The density, by the way, are bounded away from 0 at infinity, and when epsilon goes to 0, they go to the unperturbed density, what one expects. Then we have some kind of variational principle. So basically, for us, the integral of the logarithm of the multiplier is what we call the expected pressure, what we did with Carlangelo and Benoit 25 years, 30 years ago probably. And we generalize it to the quenched setting, and we prove that it is equal to the entropy plus the integral of the logarithm of the potential, and the entropy can be defined as usual in this random setting. And then we were able also to construct what we call randomly conditional invariant probability measure, because as soon as you have a system which is open, even in the deterministic setting, what play the roles of the invariant measure is the conditional invariant measure, which is in the random setting means exactly what I wrote here. So in order to understand what it means, you take some measurable set. This measure on the fiber sigma and omega is equal to the measure of this set, the set which is sent on this fiber divided by the measure of the fiber itself, because you have to keep track of the points which are not in the hole as well. And we were able to construct this measure here. And also, just a second, because I think I forget one. No, it's fine. Okay, here, wait a second. No, it's okay. This is, yes, this is a variational principle. Then we have this measure here. Okay, then we can construct a measure which lives on the surviving set, and this measure, which is mu omega epsilon, it enjoys the curve correlation, which are exponentially fast. And you see, with our uniform condition, we are able to get this parameter C, which doesn't depend on the noise anymore. And for this reason, we can get the limit theorem now. And the limit theorem are coming now, but with a limitation. So the point is, this result, we have the curve correlation. C doesn't depend on omega, but we are not able to get the curve correlation for any epsilon because it's written here, the reason. We cannot apply our previous technique using the Nagai-Givarchy technique, because we cannot prove, it is pretty annoying, we cannot prove that the operator, perturbed operator, on the Banach space constructed with this conformal measure, depending on epsilon, is quasi-compact. We cannot prove it. Excuse me, Scott, we cannot compute the compact injection in this space. Okay, so basically you have...
What can't you prove?
No, okay, when epsilon is positive, we cannot prove that this strong space is compact injected in the L1 with respect to the conformal measure. We cannot prove it. If we can prove it when epsilon is equal to 0. Yes. We cannot prove it when we can prove it when epsilon is equal to 0. We cannot prove it when epsilon is positive. As for this reason, we cannot prove that the operator is quasi-compact. And so for this reason, we cannot apply our technique.
So you're using this Romanian paper?
Yes, exactly. Okay, we tried, and okay, it doesn't work. It worked with epsilon equal to 0 because the conformal measure is basically, I mean, it behaves like Lebesgue in some sense. The BV norm constructed with the conformal measure and the BV norm constructed with Lebesgue are equivalent, but not when epsilon is positive. I mean, we are not able to prove it when epsilon is positive. So for this reason, we cannot get the limit theorem in this case. It's pretty annoying. But in the case when epsilon is equal to 0, yes, we can get a bunch of results. If I have a few minutes, let me give you an example. 5 minutes. Yes?
There is a weakening of this anion Nussbaum theory by Duder, I don't know if which there is a slightly weaker requirement. Instead of having compactness, you just need that you can extract converting sequence or something. I don't remember exactly the thing, but it's a weakening.
Okay, we have to tell Miro because probably it could answer your question.
Even when the operator is not continuous in the weak norm.
Okay, good.
You know if this can be of any help.
Yeah, of course. Yeah, probably yes.
If you didn't look at it, maybe we should look at this variant.
You mean for the young towers?
No, it's a paper by Duder, Keller, and someone else. It was done for a system with coupled mathematics. So I don't remember the name.
But if you remember, you asked you a few months ago if we have compact injection when you have a generic BV norm with respect to some measure which is not Lebesgue. You remember? And we were not able to get to find in the literature any result of this type. So for this reason, for the moment, we state the theorem only when the perturbation is 0. Okay, just a very easy example. Okay, so as an observable, we take what people usually do in extreme value theory. So we take this function here, and you see immediately that the hole becomes a ball around a center, which I call V omega naught, which is just a center which moves randomly, and with a radius which is given by E minus Z n omega, as Z n omega is just the threshold which can be constructed in order to get the limit, because don't forget in the extreme value theory we have some freedom in the choice of the threshold. They are not prescribed. You have to find it, to find them in order to get what you want, which is just an exponential asymptotic law. So here we can move the center randomly, and also this exceedancy Z and omega randomly. And here is a particular example. I take omega, which is a sequence of 4 letters, and the map is just the double shift, and with a Bernoulli measure, for instance, very simple. And then we have some grammar on the choice of the center, which is written there. So we have 4 centers possible: V1, V2, V3, and V4. V0, V1, V2, V3, and the map, which are 4 maps again here, must verify the condition 8. So they must move one particular center into the others. There are no apparent periodicity in the condition 8, because the idea is to get an extremal index which is not 1, because as soon as it is not 1, it becomes you are looking to clusters. Cluster means you have points where the maps spend more time than in other points. With this kind of prescription, we were able to compute not all this quantity which I called before Q omega k, but only the first 2. Here is the first one, because they are computable, but they're very long. They are infinitely many. It is enough to prove that at least one of these quantities is positive, because this extremal index is less than 1. It means you have cluster in your dynamics, as if periodic points were there. But here we don't have periodic points because it's a random dynamics. Still, you have this clusterization. And this would be interesting for physicists because they use this kind of technique in order to get some region in the phase space, which they call rare events, where the dynamics is stuck more than in other places. But usually this happens when you have periodic points or periodic lines which are invariant for the motion. So you stay close to periodic points and so on and so forth. But here we don't have apparently periodicity. Still, with randomness, we can create this clusterization of points. Okay, just one final word. Now the idea here is to go to the next step. So basically look, instead of looking to this first heating time in some region to look at the number of times you stay in some region given some threshold, which is called the Poisson-like statistic, as in the previous talk in some sense, and also to generalize all this theory to higher dimensional cases. But as I told you, there are problems here. In particular, these measurability issues, which were more or less easy here, but could be very complicated in the higher dimensional case. Okay, thank you, I finished.